Okay, this recording is actually meant to really be a prelude or right before we discuss the solution to number 32, which is a mixture of multiple acids and bases in the solution. And I find this one of the harder questions to actually solve, and I just want to discuss a few things before I actually go through it. First of all, you already know that in a mixture of acids and bases, we always react the strongest acid with the strongest base. All right, so definitely if I have more than 2 acid and base couples, or if I have, up to 3 species, I will definitely first put everything on a pKa scale of increasing order starting from 0 to 14, put all the strong acids as a couple H3O plus with water, and all the strong bases as a couple OH minus with water with a pKa of 14. Then look at who are the species that you have in solution. So you would circle whatever species you have in solution so you know who will react with who. And then you will look for whatever the reactions possible in your solution. So let's say I have OH minus, HA, and H3O plus. You would say, and you will choose the reaction that is first the strongest base with the strongest acid, okay? The greatest gamma. We call this the most advanced reaction, and it will proceed before the other. Okay, a reaction does not prefer to go if it's in the anti-gamma direction, and so we would not choose those as a preceding reaction. Okay? Now, once you chose the reaction and you want to determine, does the reaction, how can I do reactions? Minus X on the reactant side, plus X on the product side, then to solve, look at the K reaction. If it's greater than 10 to the 4, simply use stoichiometry on the reactant and product side and react it as if it's complete so that the reaction goes till the end. And so you have an end product that's 0 on the reactant side. If you have a K reaction between 10 to the 4 and 10 to the minus 4, then always set up an equilibrium and solve for the X. If you have a reaction where the K reaction is less than or equal to 10 to the minus 4, then assume that X is negligible for the forward direction. Okay? That's where really the K reactions become helpful, is to decide how to treat that X and how to solve the equation. It's not as helpful to know if the reaction goes in the forward or in the backward direction. And to do that, you need the difference between Q and K. Okay, so there are several reactions which are always possible, what we call successive or simultaneous reactions. And what is a successive reaction? We're going to discuss successive reactions in a type of example where I have already in my mixture some OH minus, H3O plus, and HA. H minus, H3O plus, and HA. That's what I have. Who do you think will take place first? Of course, the strongest acid with the strongest base, and yes, it's going to be the OH with the H3O plus, the strongest with the strongest, and they happen to be too strong. And then if there's any leftover OH minus, indeed, then the leftover OH minus will react with the HA. Now, if you look at the K reactions separately for each reaction, let's look at it. In the first case, let's call it K1. For this reaction, look at it. It's indeed the opposite of the autoionization of water, and therefore it's 1 divided by Kw, which is simply 10 to the 14. That's a huge K reaction. That's very large. So that's going to be definitely one-way direction. I don't treat it as an equilibrium, one way. Okay? And therefore, how do I do this? If I have some initial concentration, or initial moles, and usually with reactions we treat, it's better to use moles, initial moles, and then we would have final moles. Okay, there is no equilibrium needed. And then if we see how many moles of OH minus are left, that will sit there and react with the OH minus, with the HA plus, sorry, the excess amount from the first equation. Let's look at the second equation, the K2. K2, look at it. That is simply, look at A minus plus H2O in the opposite direction. Oh, that's exactly 1 divided by KB. Okay, because the opposite way is simply my KB for A minus, which is Ka divided by Kw. Clear? And in the majority of cases, again, by the way, if you look at most of these, Kw is on the denominator, so definitely no matter how high or low my K is, most of the cases, this will still be a fairly high K2 number. And indeed, you will notice that always, if I have a strong acid or a strong base on the reactant side, my reaction K will be fairly high. And in most cases, or in all cases, we will treat it, us in this course, as long as I have a strong acid or a strong base, as a one-way forward direction. Okay. So in the majority of cases, again, in this case where I have a strong with strong, that reaction will be higher than 100 K, K2 of the second reaction. And therefore the first starts, finishes, and then the second one starts. So we find the balancing of equation from the first, and then when we move on to the second equation. In the cases we have two simultaneous reactions taking place at the same time. This is a bit rare for this course to actually see, and to be honest, you won't see it. But the idea of such a thing is, if I have a reaction, reactants B, A minus, or in solution, I have a mixture B minus, A minus, and H3O plus. Clearly, the strongest base here between these two bases is the B minus. That will react with the H3O plus first, and then the A minus will sit there and react with the H3O plus. However, let's look at each reaction rate, not rate, equilibrium constant. And so this is going to be K1. If you look at this reaction, this is simply the opposite of the Ka expression for HB. And so it will be 1 divided by Ka. And similarly for the second reaction, this is 1 divided by Ka of HA. All right. If the Kas are close to each other for the two acids, then we will see that the Ka1, let's say, is greater than Ka2, but not by 100 times, then I can't simply treat the first one and then go for the second. Okay? Then it will be successive. In this case, if the one is greater than the other, but not 100 times more, then the two reactions proceed more or less simultaneously. Sure, the first one starts, but as B minus in my solution decreases in amount, maybe the A minus jumps in, but I still don't have 0 B initial. We have to work on a global equation, which is actually a summation of the two equations and a multiplication of their two equilibrium constants for a K global equilibrium constant. We never see that in this course, okay? Just as a reminder, anytime I have an HA in my solution and an A minus in my solution, so a couple, as long as I have a couple, then what we can say is from the Ka, we can derivatize, take the minus log of both sides and take the log of H plus, put it on the opposite side. Then you will see that we can derive what is called the Henderson Hasselbach equation, which is very useful for whenever I have a solution in the end where I have A minus in solution and HA in my solution. That being said, let's move on to doing one of the hardest problems I find in this course, number 32, not part A, part B. Part A is not so bad. Okay, so part A, it's a 0.1 mole of ammonium chloride plus 0.5 mole of ammonium acetate. So first of all, we're gonna look at that type of a problem, and then part B, and what they really want is determine the concentration of species present, and for each A and B, consider a mixture which contains solution A is separated, guys, from solution B, okay? They're not like within the same solution. A is one question and B is another question. So what they want us to determine is what is the reactions that's gonna take place between the two, and determine the concentration of all of the species present in each of these mixtures, and calculate the pH in the case of the second mixture. Well, I'm gonna calculate the pH of, you know, each separate. Okay, so part A, we have ammonium chloride. First of all, every time you'll have a species in your solution, you have to decide, what is this? What is this material? What is this compound? What is this ammonium chloride? I have to split it up, okay, into two separate entities. This is a salt, okay? Ammonium chloride is a salt. When it splits up separately into ammonium and into my chloride ion. We know Cl- is a spectator, so pretty much I don't have to worry about its existence even in my solution, other than the fact that it exists and it has a concentration. And of course, what is the Cl- concentration? It's gonna be simply 0.1 mole. That's it, that's all I have to do, because it is the conjugate of HCl, strong acid, and all anions of the conjugates of those strong acids are spectators. I'm left with this ammonium, which can react as an acid, of course, because it has a proton which it wants to donate. My other species, what is it as well? It's a salt of some cation and another cation, and an cation is ammonium, and the anion is CH3COO-. So you split this up. Of course, it requires a solution to split up in solution. Now, okay, what is the total? Now, everything is now mixed in my solution, right? So I have these ions of the two mixed in one pot. And it's forming a 1 liter solution. So finally I could get a concentration here. So I have 0.1 moles of ammonia from here, 0.05 from this side. And so I have total 0.15 moles divided by 1 liter solution. So that's 0.15 molar. And my acetate ion will be 0.05 because there's nothing else other than that. So that's 0.05 moles divided by 1 liter solution. What is this? What can these guys do in my solution? So these are the main species, because Cl- as if he doesn't exist, he doesn't do anything. He's a spectator, he looks at everything. What can these do? Can they react with each other? Or are they a mixture of bases? Are they a mixture of acids? What is this acetate? It's a base, right? This minus can act as a base. What is the ammonia? It's an acid. It can act as an acid. So clearly I don't really need it's just two species, but I'm just gonna put them on a pKa scale. Here's my ammonium and here's my acetate. So if I sit there and do this reaction, anion with the acid, so I always start with the base and then I go wherever the acid is. If I react them with each other, okay, this is anti-gamma. Anti-gamma. Will they react? Well, if I put them together, acid with base, I mean, I can set up an acid-base reaction to give me NH3 plus acetic acid. And if I sit there and do the K reaction, even if I didn't put it on the anti-gamma, let's say I decided, okay, let me do this. Get the K reaction, remember, I put the pKa of the acid on this side, pKa of the acid on this side, and the K reaction will be 10 to the power 4.5 product acid minus reactant acid, so minus 9.25. This is 10 to the minus 4.5. And indeed, this reaction is limited. As written, as I have written it, it's limited. And because I don't have any products, that's all I have as reactants, I cannot go further. Usually, I should stop here. Nonetheless, if they ask you for the pH of this system, if you were asked, I mean, I wasn't here, but if I was asked for the pH of this mixture, even if this reaction hardly proceeds, okay, it's very much limited in the forward direction. As limited as it is, I could still find the very small amount of products, since Q is less than K, because what's Q? I have 0, 0 on the product side. So Q is 0. So the reaction has not reached equilibrium yet. Okay? No matter how small this equilibrium constant is, it has not reached it. And, okay, this is just showing us doing the calculation of the K reaction, but in the long way, I don't really need to do that, show you that. But if I was asked, again, like I said, if I was asked for the pH, then I would say, okay, no matter, I put the concentrations, I would say minus X plus X, and plus X on the product side, I have 0 on this side. I have to sit there and find my X. Let's do that. And the first thing you would ask yourself, why am I bothering to do this? It's limited. Well, because I have to. Why do I have to? Because if I am asked to find pH, then I have to have the two couples, an acid and a base couple. Okay, so, but the beautiful part, so this is products divided by reactants, right? Products, X times X divided by reactants. So 0.15 minus X and 0.05 minus X. The beauty about when reactions are limited is I can say that. That's the beauty about it. And that's how I will always do that. If my X is, K is less than 10 to the minus 4, X relative to a certain amount is negligible. Clear? Great. Excellent. Now, once X is negligible, the calculation becomes much easier to do, and I do not need to do a quadratic. Okay? Now, solve for X. Okay, this is just numbers. Solve for this X. It becomes easy enough to solve. You don't have to do a quadratic. What you end up getting is the concentration. Once you have the X, you have the concentration of all the species in your medium. So what do I have now? I have a couple, ammonium and I have another couple, acetic acid and the acetate. I have two couples in my solution. And if I'm asked H, I use Henderson of each couple. So I take the first couple, pH would be pKa plus log of the ammonia divided by the ammonium. And yes, I have found this, as small as it is, I have found it. So you have the pKa, put the concentration of each ammonia and ammonium from this reaction, limited reaction, get the pH. As well, I have another couple, which is my acetate. You can get the pH as well, and you should know that the pH from either couple should be the same. Why? Because this is the same mixture, okay? This is the same mixture. This is, all of these are in one single solution, okay? So I can't have two different pH for a single solution, which is a homogeneous solution. I can't have two different pHs for it. Okay, so now calculate the pH of the mixture of the weak acid and the weak base at any concentration. Great. So look at it here. If I look at this, and this is a procedure, guys. If you have two couples, right, I can do each separately, pH of each separately, or just choose one and you get the pH of the system. And remember, in my previous recording, I said that if the concentration here of the acid and the base was the same, and the concentration of the products are the same, then simply we use pH equals half pKa1 plus pKa2. That was in my previous recording. But if you notice here that the concentrations of my reactants are not the same, but yes, the products are the same. But still, here I cannot use that because the concentration of my reactants are not the same. So I cannot use simply pH equals half pKa. I have to do it this longer way and choose maybe just a single couple. Or use the overall equation, which is adding the two pHs from these two systems, or these two couples. So this becomes 2 pH, because the pH has to be the same, equals pKa1 plus pKa2 plus the log of this system, which is, if you add the two log values, you multiply the insides. So this becomes the concentration of the ammonia times the acetate divided by the acids. So it's actually the bases of the couple divided by the acids. So this is the base of the couple ammonia, and this is the base of this acetic acid couple. Okay, so the bases divided by the acids. And if you go back to my salts, okay, if you go back to salts, I did put this equation in, and that's at the time when I told you I can't really derive it yet in details. And the reason is because we hadn't really taken the Henderson. And we still honestly haven't taken the Henderson yet until I get to the buffers. That's when you'll really understand the Henderson-Hasselbach equation. Nonetheless, this is the overall equation that I can use for any acid-base mixture where I have two couples. I just put 2 pH equals pKa of one of the acids, pKa of the other acid couple, plus the log of the bases divided by the acids concentration. Now, it would be wonderful if something cancels. So in this case, the products, whatever's on the product side, is canceling because they have the same concentration. And then you put the reactant concentration in there. Okay. And so this becomes whatever the reactant concentration is, which is CH3COO minus divided by the NH4 plus. Once you plug it in, you will see that the pH is actually equal to 6.7 as well. Try it out and you will see that it's exactly the same as that. What would I do? I would just choose one couple and solve the pH from there. Okay, that's what I would do. And or, actually, no, that's not what I would do. If the products, look at this, if the products are the same, look how nice this reaction becomes. If the product concentration is the same, and here it is, then and X is negligible, so when the K reaction is less than 10 to the minus 4, that means this X is negligible. Then simply I use this equation, pH equals half pKa1 plus pKa2 plus half of the log of the concentration of the base in the mixture divided by the acid in the mixture. Okay, it becomes easy to do because then you don't have to do the calculation of X even. Okay, then I don't have to calculate X. Here it becomes much easier because you already have this number without X calculation. Much faster. Okay. Now, the second part. 0.2 molar of phosphoric acid, some KCN reacting, and okay, so first of all, put everything on a pKa scale because we have definitely 3 reactants taking place. So definitely I need a pKa scale. KCN, you already know that this is definitely a salt, which splits into K plus and CN minus, and CN is a significant material because it's not the conjugate of a strong acid, so it possibly can react with something. Okay, then what do? Then decide, okay, who are my species? Circle them in my system. And here they are. I circled them on my pKa scale. Okay, and there's your species. Now, notice H3PO4 is what I have, yet on my pKa scale, I also include all the other degradation species for the triacid. So H3PO4 becomes H2PO4, and then the H2PO4 becomes HPO4 minus, and HPO4 2 minus becomes PO4 3 minus. Why did I include that all? Because the minute I have H3PO4 in my mixture, unfortunately, I have some of the rest automatically. Okay. And plus H3PO4 is one of those acids that has a fairly high pKa value relatively, okay, relative to others. Great. What is the most, the dominant reaction that will take place in this mixture? So first of all, I have 2 acids and a base, okay? So the only thing that can take place at the moment is, and notice I didn't put water nor H3O plus because they're not in my system, okay? I do have water, but it's the weakest of acids or bases. So I don't really put it on a pKa scale so I don't get confused of what species we actually have. En minus is my only base. So regardless, by the way, in the gamma, against the gamma, no matter what, this base will react with whatever acid is in my system. Okay? So Cn minus, which we saw in the previous question, Cn minus with H3PO4 has the greatest difference in pKa. That will be my strongest base, and H3PO4 is the strongest acid in the system. The first reaction that will take place will be between the H3PO4 with the Cn minus, and clearly just from since I have this already on a scale, this becomes H2PO4 minus with HCN. Done. Okay, what's my K reaction here? Do I need to write a K reaction? Yes, I do. Okay, because I need to now know what do I have in my solution and how do I proceed. Okay, you do the K reaction, look at the products, pKa of the products, pKa of the reactants, sorry. A reaction happens to be 10 to the 6.8. How do I know? I have pKa is 9 minus 2.2, which happens to be 6.8. Okay. You could also put it Ka scale. So Ka of the acid on the reactant divided by Ka of the acid on the product side, and you get your K reaction. Huge, relatively, it's greater than 10 to the 6, so definitely complete. What does that mean to me? It means that if I have reactants, 0.2, 0.2, that's it. This is going to be a complete reaction. I don't do a setup of an equilibrium. I don't do minus x plus x. I simply say reactants will be 0 or a limiting reagent. I look who's my limiting. Oh, they both have the same moles. Usually it's a moles reaction. So they have the same moles. And therefore, if you have a different volume, go for volume, multiply it. We'll see in titrations, we see that often. When we get there, we get there. For now, this is 0.2, 0.2, it's the same. So there's not gonna be anything left over out of them. And all of them will become converted into 0.2 and 0.2 of the HCN. Now, if they are different here, we take the excess reagent, okay? That will be left over, and we take the limiting moles is the one that's gonna be the change. Okay, so the product will be only the limiting amount. Always, once you're done with setting up the first reaction and finishing with the first reaction, it happened to be complete. We're happy with that because it makes my calculation easy. Then ask yourself, what's my now new leftover solution? What's my new solution? And write the species that you have. Your new solution is a mixture of HCN, H2PO4, and some 0.05 moles of acetic acid, which I didn't do anything with. I haven't reacted with it, okay? First thing, you're gonna ask yourself, so how is my H3PO4 going to react? How is it gonna react? What can it do? This is an acid, HCN is an acid, and acetic acid is an acid. What about H2PO4? What is it? Well, it can be an acid, but it can also be a base. It's amphoteric, right? So how will it react with these two acids? Well, either I can have a mixture of 3 acids, or I can do another reaction of this H2PO4 acting as a base while the others are acids. And as long as I have acids in solution, the H2PO4 will act as a base, hopefully, okay? And hopefully that base is, at least with one of them, a spontaneous reaction. We're gonna have to see if it is a spontaneous reaction, if it reacts. Okay, so I just put this on a pKa scale again. I drew out a new one. And now I circled the species in my new solution, okay? So we have the new solution, we have HCN, H2PO4 minus, and H3 acetic acid, which hadn't reacted before. Notice I circled the H2PO4 twice. So again, we have either a mixture of 3 acids, or this H2PO4 reacts with one or the other of the other acids. If it's gonna react with the acid, so it's acting as a base, with which acid will it react with? Yes, it will react with the stronger acid, which is the acetic acid. But look at this reaction. Here's my base. Again, this is how I do it. I always start with the base, go to the acid, anti-gamma. Anti-gamma, that doesn't form a gamma to me. That's not like this, okay? Okay, anti-gamma, that way, oof, oh, yucky. Not the most, spontaneous reaction, but, better than nothing. Let's set up this anti-gamma H2PO4 in acetic acid. So what's the K reaction here? Okay. The reactant acid is acetic acid, the product acid is H2PO4. So it's the pKa of the acetic acid divided by Ka of the H3PO4, which happens to be 10 to the minus 2.5. Let's look at it now. What about this K reaction? What does that tell you? Well, it tells me that I have to do a reaction minus X plus X. I can't do it complete, and it's also not limited. Darn. If I could, but I can't, okay? I have to do minus X plus X. Of course, we did that, and it's not complete, and it's also not negligible. What does that mean? It means I actually have to go ahead and do a quadratic equation and get a solution for X. You have to do that, okay? Now, yes, indeed, this X is not that significant. I mean, 10 to the minus 2 is not that much, but, just our rules, that's it. It's not negligible, okay? So solve using a quadratic equation, and we cannot neglect it. Once you do a solving, get all the species in your system, okay? So who are my species? I get the H3PO4, which is simply the same as that's my X, and get all the leftover acetic acid and H2PO4 in my system. Once you have those, what do you have? Well, don't forget, I still have some HCN and H2PO4, okay? And one of the questions that I always had is I still have some H2PO4 left, which is 0.125. Okay, will that then react further with my HCN? Well, a very high anti-gamma in that direction. If it does react, it's very much negligible. That X through that reaction is very negligible. So I'm sure it probably will react, but it won't remove much of my H2PO4 concentration further. Not much will be going further beyond this, okay? Once it reacts with my leftover acid HCN. Here, great. So these are my reactants and my species. Of course, I have some still HCN 0.2 molar, but they don't affect my reaction too much. And so what do I have to do? I have to, of course, I was asked for pH. So if I'm asked for pH, I can choose either couple, the H3PO4 with the H2PO4 couple, which I found its concentration, or I can choose the acetic acid couple, and I find its concentration, which I found its concentration. Use Henderson because I have a couple base and the acid. In this case, can I neglect anything? Again, I could have neglected my products, okay? Could have neglected my products. And what about my reactants? What about my reactants? Just as a curiosity, let's do this. Neglected my products. So here is my net, the summation of the two equations. So this is 2pH equals pKa1 plus pKa2 plus log of the bases divided by the acids. Again, the products happen to be the same concentration, so I could get rid of those. What about the upper part? Can I keep them as the initial concentrations? Well, look at this. This was 0.2 and this was 0.5. It is a ratio. And I'll be honest with you, this ratio didn't vary too much once the reaction took place, because remember, my K was not that very high. And honestly, had you just kept the initial concentration 0.2 divided by 0.05, you would have gotten the same pH value. But still, this is the more correct way of doing it, is actual calculation of the X. Though it is small, this is the more detailed, correct way of doing it. So my pH happens to be 3.79. Of course, this would have been the same solution. And here, unfortunately, we still had to solve for X. So I'm not saving any time by this reaction. Great. I find this one of the hardest questions in the whole course, to be honest with you. And it took a full lecture for me to actually solve it for you, but there it is in its details.